gray on Wednesday, as I said. So in general, it's good for the second part. Some of you didn't do very well, but I will talk about that on Wednesday then. Okay, so save for Wednesday. By the way, yeah, please wait for me just a few seconds. Let me close it. Okay, so let's come back to this slide. I think that last time we stopped at slide number 23, and hopefully you remember that example, right? It is a very good example, and today I will go over with you one more example for you to pay attention to the important things for this chapter, right? So first of all, you have to know what is the purpose of interrupt, right? So, I mean, for the final exam, of course, I mean, interrupt is you in what cases, right? For communication, for multitasking, for signaling something bad happened in the processor, for example, division by 0, something like that, okay? So, you should know all of that. And when interrupt happen, then you really have to know the process, right, from the beginning to the end, right? So the first thing it happens is the processor will look for the address of the interrupt service handler, right? Kind of a subroutine that will be executed automatically whenever that kind of interrupt happens, okay? And then when it finds the address of the subroutine, it will go. Oh, but actually, even before that thing, during that process, it will push A registers, right, to the stack, right? So A register probably you know already. So we will all go over these A registers, and the stack that it will go to one of the two stack only, right? So either it is the main stack, or the process stack, right? Later on, you will see that for process stack, you may have many. But for now, just remember that we have two stacks, right? So the main stack and the process stack. So before interrupt, if the program is using the main stack, the A registers will go to the main stack. Before interrupt, if the program use the process stack, then at the beginning of the interrupt, these A register will be pushed on the process stack, right? Just remember this important point. And how do you know? How do you know it will go to the main stack or the process stack? Do you know? You just look at one bit, okay? Bit 1 of the control register, right? Look at that one. And if that bit is, okay, let me come back. It's easier for you to remember. Yeah, so look at the bit number 1 of the control register, okay? So if that bit is 0, it means that is the main stack pointer is used, and if that bit is 1, the stack pointer will be used. And this bit is actually appear in the LR register as well, right? Remember the value FFFF. Let me go to here. Yeah, the value here FFF9 and FFD. So you can see the bit number 2 in this number will indicate it is MSP or PSP. Bit number 2, okay? So that's why you can see if that bit number 2 is 0, meaning 9 over here, it will indicate the main stack is U. So when you exit the subroutine, you have to pop out of the main stack, okay? If it's D, you can see the bit number 2 of the LR register is 1, right? That indicates the process stack is U. So when you exit the handler, the interrupt service routine, then you have to pop the A registers out of the process stack, not the main stack. Okay. Okay, so with all of that, this is just a review for you to do the example. Okay, so if you can do the example, then it will be very, very good. Okay, so let's start from here. Let's start from slide number 24. This example. Okay, wow, there are tons of things. Very crowded slide over here. So first of all, you have to pay attention to something, right? To on the right, that is basically the memory, and to be specific, it is a stack area, right? The stack area over here, and it's the stack pointer at the beginning. It has the value of 20000200 up here. So the stack pointer point up here, right? And this is the main stack point, main stack, right? And this is the main stack pointer has this value over here, right? We don't. In this case, when interrupt happens, at that time we are using the main stack pointer. Okay, so you will see that the A register that we will push in will go to the main stack over here. Okay, so that's the one thing to pay attention. The second, in the middle over here, these are registers in the processor. Okay, not in the memory, but this is a processor, right? And you already know all these registers already. We have 13 general purpose registers. We have some special one that you know, for example, the stack pointer over here, link register, program counter, the program status register, right? These are very important register over here. And you have and the stack pointer over here, the SP over here shows the current stack that we are using. So in this case, you know, MSP over here meaning we are using the main stack pointer when the interrupt happened. Okay, so on the left side, it is the code, right? So you have a main program over here, right? And you also have a interrupt service routine, right? So when system when the system timer generate an interrupt, this handler will be executed. Okay, so that's the setup for you. And now let's do together. Let's do this example together. So we will execute the main program from here, for example. And then when we go down to this instruction, right? So interrupt happen, and the address of this instruction is this. So that's why you can see that in PC, right? At that time, the value here is the address of this instruction. Okay. Now, what happened? What do you think? Interrupt happened, right? Then first of all, we have to push, not we, but the processor will do automatically, push A register, right? To what? To the main stack in this case, right? So you will see that which one is the highest register number? This one, right? So this one, I mean, PSR will go to there, right? And then PC will go to here, and then LR, let me see, 1, 2, 3, and then R12, R2, R1, and R0. Okay, so let me move to the next page, and you will see all of that values will be pushed on the stack. Okay, 1, 2, 3, right there. See, right? So PSP go up here. You can see PSP before, so go up here. PC at that time is 44, right? The address at that time. We really have to remember the PC over here, so that when we exit the handler, the service routine, the interrupt service routine, we will come back to this instruction in the main memory, okay? In the main program. And then LR, okay, so we save the old value of LR. And the very special thing, in when it jumped to the interrupt service routine, the value in LR is a special value, right? It's called exe return value. Okay, so you can see that's a F9. Okay, So either it's F9 or FD in here. Okay. So of course, for the case of if you don't have the floating point unit over here, so for this chapter, please just remember these two values for me. You don't need to remember more. So later on, when you are out there in Silicon Valley, if you work for some other company, then at that time you can look at the reference book and you will see that there are a few more. Okay, not just F9 and FD. I think there may be just 4 or 6 values that you need to remember. Okay, so in this class, just F9 and FD for me. So why is F9? Do you know? Did you know why F9 is in here? Oh, because we use the main stack pointer, right? We use the main stack to store all these A register value over here, right? So that's why it's F9. If it's a process stack, this one will be FD. So pay attention to that. Okay. What else do you pay attention to here? Okay, right here. So look at the main stack pointer, right? So before the value is 2000,200. Okay. But after pushing all these A value, the new value of the stack pointer, the main stack pointer will be here, 1E0, right? So that's changed. So I just want to bring your attention to that. And what else should we pay attention? This one, PC, right? So PC will point to the system tick handler, right? The interrupt service routine. And that the first instruction is 1C over here. That's why the PC will point to that one for the processor to execute this one, right? Start to execute from this instruction. Okay. By the way, this is I already said about it, but I just want to point to this one for you to pay attention to that. Okay, so now let me move to the next slide. So the next slide will be basically we execute this instruction and we will jump to this one, right? And the difference from the previous example is inside the interrupt service routine. Okay, we also call another function. This is new. Before we didn't do that. But now, basically, we like to have some more complicated example for you to see if you can understand the whole picture over here, right? So pay attention to that. So let me see. Let me move to the next slide over here. Okay, so this instruction, we just finished this instruction. So add 1 to register R4. So that's what R4 before was 4. Now it is 5. Okay. Now the next interesting thing is the it branch and link. Okay. It will jump to a function. I don't know where that function, and that function is function with a name with the label psi, function psi, probably to calculate the psi of some angle or something, right? And okay, so let's jump to that. Let's move to the next slide, right? But you can see the PC point to that instruction over here, so it will be executed next. Okay, 1, 2, 3, jump to there. Okay, so assume that the psi function reside at this address. I mean, A is 000F0, right? So that's what PC point to that. Okay, and what else should I pay attention to? This one. Okay, and because you this is just a regular function call, right? So whenever you call something, the address of the next instruction will be stored in the link register, right? So you can see 24 right there, right? But there is a problem. I don't know if you can recognize the problem. Somebody can tell me what is the problem? So before calling the function sign, right? The link register has the value F9. The value F9 is very, very important for you to return to the main function, right? because this value will tell you, okay, I have to unstack the main stack over here, bring it all back these A register, and among the A, we also have the program counter over there, 44 over here for me to return to the main function. Okay, now it seems to me that when you call the function BL, right, you destroy this very important value. See, now this value is 24. Okay, so that is the problem, right? So if you destroy that value, then when you go down here, right, branch BXLR, you want to return back to the main function, you cannot return because you destroy this value. I don't know what to do. Okay, so let me move on and you will see the problem. Okay, so now if I move on, the PC will point to here, and the interrupt service routine is about to end and about to jump back to the main function, right? But at this point, it is expected to have something like FFFF9 or FFFD, and we don't have that one anymore. We destroyed that. Too bad. Really bad. So how to fix the problem? Please give me a solution. Somebody let me know how to fix this situation. The problem here is because we destroy the value FFFF9, right? Oh, thank you so much, William. That's exactly what it is, right? So before doing anything, before calling this function, we should save that important value, right? FFFF9, at least somewhere else. That's William just said, at least somewhere else. And that somewhere else is, why don't we use the stack to store them, right? The stack is a piece of memory over there, and you can use that one to store, right? So, and you will see that's exactly what we will do on slide number 29. Okay, so on slide number 30. Okay, so when you go to the service routine over here, right? Interrupt service routine. So at the beginning, before you do anything, right? In this case, you save it onto the stack over here, okay? By using the instruction push LR, right? So, and then when you do the function call over here, it will remember the address of the next instruction 28 over here, right? So when you're done with the function sign, it will go back to the 28, okay? Right? And when it executes 28 over here, right? It will pop out the value, the important value that you say. That's FFF9 over here. Wonderful, right? So it will bring this value back to the LR for you, right before you end the interrupt service routine of the handler, right? So by this time, the LR register will have this value, right? And then you call this one, then you execute this one. So when you execute this one, you will return back to here, okay? Because this value will tell you that please, when the processor sees this value, it will automatically pop out these A register, right? From the stack over here, from the main stack over here, okay? And put it back into these registers over here. Among them, there is one important register, that's the program counter, okay? Ooh. Okay, something wrong with the program counter over here. So let me check. Oh, this should be. Let me check this value, okay? And I will fix it later. But I mean, among these, should be 44 something. Should be 44. What? Okay. Let me check that one. Okay. So let me check the PC over here. So PC will finally we will after popping out the PC, we'll know how to return back to back to the main program over here. Okay, so after the lecture, I will reject the value over here, and I will fix the slide if necessary, only for this item. Okay, so so that's all. That's all for the interrupt, calling, stacking, unstacking, all these things. Okay. So now we move to the new. We go to the new topic over here. That is enable and an interrupt. Okay. So before going to this part, I'd like to remind you, enable doesn't mean that's execute. Okay. Like if you have an electric fan, for example, right? Enabling is like plugging into the cord into the outlet. Okay, plug into the outlet just to enable it, right? But when you actually execute the interrupt, is when you start to press the on button. Okay, so enabling doesn't mean that the interrupt service routine will execute right away. Okay, it doesn't mean like that. You just enable them. It's like plug into the outlet, plug in your electric fan into the outlet, but not pressing the power button yet. Okay, okay. So just remind you that. As you know, for the interrupt, you have two types, right? The system interrupt and the peripheral interrupt, right? So system interrupt, you have 16. The number is from, I forgot, -16 to -1, something like that. And for the peripheral interrupt, the number is from 0 to 239, right? Something like that. Okay, so now how to enable them? Okay, so first of all, let me talk about for each time you have a different way to enable the interrupt, right? So how about for system exception, right? So for these guys, these are very special interrupts. Okay, that's why some of them are always enabled because they are so important. I mean, the software cannot disable them. Do you know which one? For example, reset, right? Reset is so important. I mean, it should be always enabled. It should not be if you disable that one and if your computer has some problem, you cannot reset it back and then reboot again. Okay. And then for system exception, actually there is no centralized registers for enabling or disabling. Actually, for each time of the interrupt, it is controlled by discrete register, right? For example, the system tick over here, it has its own register to control to enable or disable the interrupt. Okay, so it's not centralized place for you to enable the interrupt. However, for the peripheral interrupt, actually we group them. We have a bunch of registers to enable these 240 peripheral interrupts. You will see very soon that we group them all into, I think, into A registers. Okay, so A register for each bit, for example. So so let me see. For over here, for example, today for the next few slides, I just talk about how to enable and disable them. That's all. So for enable the interrupt, remember this name, ISER. Okay, that's the interrupt set enable register. Okay, ISER is for enabling, right? How about for disabling? It is ICER, interrupt clear enable register. Okay, I will talk about these two only. Okay, so let's move to the next slide. You see. Okay, so enabling peripheral interrupts. Just remember that you have 240 of them, right? And maybe let me use one bit for one interrupt, right? And if that bit is 1, it will indicate the interrupt is enabled, right? So if so, then how many bits do I need? Please type. Please, I'd like to see your response. How many bits do I need? I have 240. peripheral interrupt, right? So how many bits do I need? Please respond. Maybe this is a true or false question for the final exam. Matthew 16. Okay. Any more answer? I'd like to see a lot more answer. 32. Okay. More. Jake 32. I'm looking for the right number. I still don't really see the right number. As 128. Still not the right number. Kristen 8. Ismail 64. None of them are the right number. There it is. Yeah. Thank you so much, Ethan. 240. That's the number I am looking for, right? As I said, we will use 1 bit for each peripheral interrupt, right? Because we have 240 interrupts, right? So you have to use 240 bits, right? 1 bit to indicate 1 bit for each interrupt, right? 240, right? So do you agree with me? And actually, I'm a bit puzzled to see the number 13 and 69. So probably you have your own thinking, but let me tell you the correct number is 240. Okay. So now I like to put them into a bit of register. These are not the registers in the processor. Okay. I just use some peripheral registers to store this bit, right? Okay. So each register has 32 bits, right? And I need 240 bits. So how many registers do I need to store these enabling bits? Okay, now that's another question that I like to multiple choice question I like to ask you. Okay, go ahead.
You said 240 interrupt, and you were wondering how many registers from that? How many registers?
I will use each register has 32 bits, right? I'd like to use some number of registers to cover all 240 bits, right? So each register I can store 32 bits. So for 240, how many registers do I need to store all 240 bits, enabling bits? William said 8. Okay, I see the number correct immediately. So yes, that's correct, 8, right? So let's see, 8 times 32 is 256, right? So more than 250, more than 240, right? So that's correct, right? But if you use 7, it's not enough, right? Let me see. Yeah. If you use 7, then it's not enough. So we have to use 8, right? Okay, so that's one step. So in your mind, you should know that we have 8 registers to store the enabling bit, right? And another 8 registers to store the disabling bit. Remember that, okay? To enable an interrupt, you have to turn on the enabling bit, okay? You have to set the bit equal to 1, okay? To disabling an interrupt, you have to turn the corresponding bit in the disabling register, okay? If you look at the enabling register, if you change from 1 to 0, it will have no effect, okay? It doesn't mean that you will disable the interrupt, okay? To disable an interrupt, don't look at enabling register anymore. Look at the disabling registers and turn the bit there to 1. Okay? Understand? Okay, so let me repeat again. For each interrupt, today I will teach you only 2 bits. Right? 1 bit is to enable that interrupt, and 1 bit is to disable that interrupt. Okay? So the bit to enable the interrupt is in a group of A register called IS. What is that? Interrupt set ISER. Okay. To disable them, you have to look in the group of registers storing the ICER bits. Okay, understand? Okay, so now this is really somebody is calling me. So please wait for me. Wait for me just 2 minutes. Hello, Professor Dutton. How are you? Yeah. Could I call you back? Actually, you know what? I'm in the middle of the lecture. Let me finish the lecture and I'll call you back. Okay? Yeah. Thank you so much. Okay. Bye bye. Oh, Professor Dutton is actually my advisor at Stanford University. Long ago. I don't know. Probably he's just called me to ask me about the situation about the COVID-19, I guess. So I will call him back later. Okay, sorry about it for interruption. So over here, okay, so we talk about the enabling peripheral interrupts over here. Okay, so you have 240 bits, right, and you put them into a register, right? So for example, if you look at this page, the number at the bottom over here are the interrupt numbers, okay? And the number up here is the number, the bit number for that register. Okay? So you can see we will have a of these register. This is a register number 0. This is a ISER0 over here, and this is ISER1, right? And then you have a of them right there. So the first register over here you can use to store the enabling bits for the first 32 interrupt over here, right? So interrupt 0 will be stored at bit 0 of the ISER0. Understand? Okay. So now, if I want to store the enabling bit for interrupt 26, for example, then I will ask you, for example, in the final exam, where do you store that bit? And you have to answer something like that. Okay, I will answer the interrupt bit for interrupt 26 in the register ISER0, okay, not 1, 0, and the bit number is 26. Okay, you have to answer that. If you answer that, then you get full credit. Okay, next question. To see it now, this time you will do it for me. Okay, I will not do it for you. Okay, so now I ask you. I would like you to enable the interrupt number 44. Okay. So can you answer me 2 questions? First of all, the first question: what registers to use? Right. The second question, the second answer you have to tell me is what bit in that register you will use to enable the interrupt 44. So tell me. Anybody tell me? Can tell me? Go ahead. You know what? Actually, this is what I asked in the final exam last semester. So now let's see if you can do it.
Okay. So the first question, figure out if we're
for the first question is actually what register you will use to sort, right? So you have only 8. You have only 8, and you know that from interrupt 0 to 31 will be in the first register, register 0, right? ISER0. So the second register will be U for interrupt 32 to 64, right? Right? I mean, to 63, 32 to 63. And then, right? So our interrupt is 44. So, of course, you have to use the register ISER1 for sure, right? This register, not this guy, and not this guy down here. Understand? So that you already answered one for me, right? One question. So the second question is what bit in this ISER1 to use to enable the that interrupt in 44. So it turned out that bit is bit number 12. Is that right? Because this is a interrupt 31 will go to here, right? Interrupt 32 will be here. Will be the first bit of the second register over here, ISER1, right? Interrupt 33 will use bit 1 of this register. That's why interrupt 44 will use bit number 12 of ISER. Okay? Right? So, okay. So that's just for you to have a feeling. So now we should go down to some formula. Okay, so if I tell you an interrupt number, probably you will figure out quickly what register and what bit for that register, right? So it's very easy. So how do I know? In this case, we figured out it's the register ISER1, right? How do we figure out this number? No problem, very easy. You just let me see. Can you tell me the formula? Hopefully you already know the formula. Okay, the formula is very easy. What register, right? So you take the interrupt number and divide it by 32, and the quotient will indicate the register number, right? The integer quotient. For example, we are looking at 44, right? This one I just added in the slide today. That's why you can see, and I uploaded several times before the lecture. So 44 divided by 32, the quotient will be 1. Is that right? Right. So that's why we know very sure that to enable that interrupt, we will pick the ISER1 register. Okay. How about what bit? What bit for in that one in that register? So it turned out that it is just the remainder of that division. That's all. Okay. So 44 divided by 32, right? So the remainder is 12. Is that right?
Isn't that modulus?
So 12. That 12 will tell you the bit number in the ISER register. Very simple, right? So two things. You find out the register number, and this one just divided by 32. Take the quotient, put it over here, and over here, this number is the bit offset. It's just the remainder, right? So that's one way to do over here. There's another way to do. Actually, divided by 32 is basically shifting to the right by 5 position, right? No problem, right? Divided by 32 is equivalent to this one, right? So you can use it over here, and the remainder mod operation, remainder of the division to 32 is you can use this one. You can use the mod symbol over here, or there's another way. Basically, you just AND with bitwise AND, okay, with 0, 1, FF. Basically, you end with the 0, 0, 0, and then 1, 1, 1, 1, 1. Okay, and you will get the remainder. So let's check with me over here, right? Okay. So first of all, figure out this one, right? And interrupt 44. The binary number for that is 001011100. You probably in chapter 2 you already learned about this one, right? You know this one very well. So if you don't remember, let me repeat it again for you. The way for this one is 1, 2, 4, 8, 16, 32, 64, 128, right? So for this number is you have 4 over here, plus with 8 is 12, and then you plus 32 over here. So that's exactly 44. Okay. So now if you shift by 1, just shift by 1, this 0 will be gone, right? If you shift 2, this one will be gone. Shift 3, this one is gone. Shift 4, this one is gone. Shift 5 times, this one is gone too. So the remaining one is actually number 1 over here. That's exactly what we want, right? So you will pick ISER register 1 for that purpose, right? So now let's check to see if this one will be U12, okay? So let's see. Now you end 44 here. You end 44 with 0, 0, 0, 1, 1, 1, 1, 1, right? So you will this part is gone, and this part is 0, 1, 1, 0, 0, right? And that's exactly 12. See? Okay, so either you use this one or you use this one in C. That will be okay to figure out where to turn on the bit if you know the interrupt number over here, right? You can figure it out. So, I mean, who knows? I mean, in the final exam, I will ask you, okay, I would like to enable interrupt 85, something like that, and you have to tell me, you register whatever, you register 3 and the bit 17, whatever, right? So that's for enabling. So for disabling, the same thing, the same operation, okay? But the register group that you will use is not ISER, but it is ICER. That's the difference, okay? Don't make mistake over here, okay? And the inside, how to pick the register in this group, the same thing. Shift right by 5. And this one is just the remainder, okay? And then you will move the number 1 over here, shift left by this bit offset, and set the bit, okay? For example, over here, right here, okay? So number 1 over here, right? If you shift 12 times, you will shift 1 time, 2 times, blah 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 blah. 12 times you will get to here, right? And you assign this register by 1 shift by 12. That's exact right here. You set this one equal to 1. Wonderful, right? Very good. So let's move on. So enabling and disabling. Now I hope that you know very clearly about this one, right? So let's move to another topic over here. That is
actually, I was wondering why is the disable look identical to the enable for a second?
Right. I understand what you mean. I mean, why don't we just use 1 bit, right? If that bit is on, it's enable. If that bit is 0,
I mean, is it like a toggle switch kind of thing, where enabling is the same as disabling? It's enabled, it'll turn disabled, and disabled, it'll turn enabled.
Oh, the sound is very bad. Can you repeat again? I don't understand you.
Sorry, I was wondering if it's like a toggle switch, so it's more like if it's enabled, then this command disables it, but if it's disabled...
Oh, I understand. So that's exactly what I said from the beginning, but you said no, so you confused me a little bit.
Oh, so, sorry, it's just the wording.
Instead, why don't we use just 1 bit to for both purpose, enabling and disabling, right? If that bit is 1, it's going to be enabled. If that bit is 0, it will be disabled, right? But that's dangerous. That's dangerous. You really have to separate them out because you know what? Because if you don't separate them out, then when you are setting for 1 interrupt, when you enable 1 interrupt, it may affect other during the transition.
I was wondering why they look identical.
Because even if you write back, for example, initially that bit is 0, right? And you want to write back the same number, 0, right? So you may think, oh, I didn't really disturb other interrupt at all. But actually during the transition, it may go before it go back to 0. It may transition to 1 and back to 0. So that's what to be sure, to be very, very sure. Disabling bit will be in a separate register, okay? And enabling bit will be in a separate register. So that's better. Okay.
So it would do nothing if we change that 1 into a 0.
Okay. Yeah. Of course. I mean, thank you for the suggestion. But probably I think that engineers at ARM, right, already thought about this.
I think I noticed. I think I noticed the difference in that one's saying ISER while the other one's IC.
Yes. We have to separate them up, right?
Okay, because it looked entirely identical, so I thought the ISER was the same on the disabled, so I didn't notice the C. I thought it was an S for a second.
See, clear. Yeah. So that's a different register. Okay. So let me move on. Okay.
Yes,
one more question from ZZ. ZZ said ISER1 and bit number 11. No, actually bit number 12. Yeah. Are you clear now, ZZ?
I think that question was done a little bit prior.
Okay, good. Okay, no problem. Okay, so now let's move on to the last topic for today, right? So that's the interrupt priority. Okay. Why do we need the interrupt priority at all? Do you know the purpose? Somebody can tell me why? Why do we? I mean, when you are when the processor is running, if you have the interrupt, okay, the processor will stop and jump to the subroutine, right? The interrupt service routine to execute that thing, and then return to the main function and continue with the main function. Why do we need the priority at all? So what is the purpose? I'm waiting for some answers here. Something have higher danger, but why? Why do we have a higher danger? I mean, each time I just have one interruption, right? And I just service him. For example, William come to me and request me to do something. I'm the processor. I will do something for him, and then Matthew come and say, "Oh, Professor, I need another thing." Okay, so I will serve the Matthew. Okay, and when I'm done with you, I mean, then another student will come. For example, let me look at the list over here. Muhammad will come to me and ask for a different type of service, right? So why do I need priority for these students? The problem is what happened if they come to me at once, right? Do you see the problem? So if Matthew, if Zizi, if William, Matthew, all of them come to me at once, so I have only one processor over here. How can I serve all four of you at the same time? So that's why I need to assign the priority number for each of them, right? So for example, Matthew Wu, he may have a highest priority because he need to because he need to go somewhere very quickly. So I really had to pick him to serve him first for him to go to somewhere, right? So that's why we need the priority over here in case of you have many interrupts happen at the same time, right? So for each interrupt, I will assign a priority number, right? So don't be confused that if some interrupt has a lower interrupt number, it means that it will have higher priority, okay? Higher priority, higher urgency. So if I have two interrupts happening at the same time, A and B, and if B has the number of 2, A has the number of 5, which one I will serve first? Number 2, is that right? B. Do you understand? Right? Lower priority number means higher urgency. Okay, higher urgency over here. So let me see over here. So if you look at the interrupt over here, you can see maybe starting from the reset interrupt over here. So up to here is non-maskable interrupt, hard fault, something blah 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 blah. And when you go to 0, 1, 2, 3, something that's a peripheral interrupt, right? The three guys down here, they have the highest priority. And of course, I think that you understand right away, right? Why, right? For example, reset has to have the highest priority, right? No matter what you are doing. If I reset the computer, it had to be reset, right? It cannot wait for anybody else, right? So that's why reset, usually the priority is very high, -3. Okay, so -3 is actually the lowest number already. Nobody has lower number than that, right? And this is a fixed priority. You cannot change it, basically. And even, same thing. Similarly, for hard form and NMI, they have a fixed number, -2 and -1. You cannot change that. Okay. However, for other, you can change. Luckily, for other interrupts, you can change the priority. How? Go to next page. This is how you change it. Okay. So let's see. So for each interrupt, let me see. Yeah, for each interrupt, we will set aside a byte. Okay, a byte to store the priority number. Okay, understand? Remember, for enabling and disabling the interrupt, for each interrupt, we just need to use 1 bit, right? Because you just want to indicate it's enabled or not enabled, right? But in this case, we have to identify, we have to assign a whole number, the priority number, maybe 1, 2, 3, 4, 5, whatever, right? So 1 bit is not enough. So for the priority, for each interrupt, you have to use a whole byte to store that priority. Okay. So this is the byte to store the priority number over here. Actually, for the last 4 bit over here, we don't use it. That's the not implement. Maybe in the future, maybe ARM will use it for some purposes in the future. I don't know. But currently, for Cortex M, we don't use this thing. We only use 4 bit over here of this byte, right? To set the priority number, right? And actually, the priority number is divided into 2 fields. Okay, the first field over here, 2 bit over here, is called preemption priority, and the second is sub priority number. Okay, so what is the preemption priority? It's actually, the meaning is this, right? For example, if 4 students coming to me, interrupt me, and ask me for service, right? So for example, I'm serving Matthew, I'm answering Matthew, okay? So and then some other student come as well, right? They have the same priority number as Matthew, right? Of course, they are pending, right? They are waiting for me, right? They are waiting, and then after I'm done with Matthew, I will look for the student that has a lower priority number, right, to serve first, right? So I will look for the sub priority number over here. However, for the preemption, the meaning is this: even when I am serving Matthew, okay, right, and Matthew, maybe for these 2 bit, Matthew has a I'm sorry, and then I'm serving Matthew, okay, and then 3 other students come, okay, and I will look for the preemption over here. So if Matthew number, the preemption number for Matthew is higher than some of the students waiting out there, then you know what? I will actually stop in the middle of the session, and I will ask Matthew to go out, and I will serve the next student, because the next student may have a lower number. Lower number means more urgency, right? So just remember that these 2 bit is preemption bit, meaning it will pick out some task, even if that task is running the interrupt service routine. I will stop that task and serve the one that has has a lower preemption priority. Okay, so just remember that. Okay, so let's move to the next slide over here. yeah, you can think about it, right? But the preemption has a little bit different meaning. Is even if somebody is already in there, right? The processor can kick that one out if if that preemption priority is has a higher number. Okay, higher number means lower urgency. Okay, so so now let's talk about the interrupt priority setting for peripheral interrupt, right? For the 240 peripheral interrupt that I just tell you, and as I said, for each priority, for each interrupt, if you want to set the priority, you need 1 byte. Is that right? Right. So okay, so let's see if you answer this question correctly. So I have for peripheral, I have 240 interrupt, right? So how many bytes do I need? Please respond. How many bytes do I need? Maybe something like 240 interrupt and it interrupt is 1 bit, so 240 divided by 8, so probably 30 bytes. Is that right? So Matthew respond first. Sorry, Matthew, you has been tricked by me. So 30 is a wrong number. Anybody can please come on, give me a number. Give me a correct number. Muhammad 8, not the correct number. As I said, for priority, we need a whole byte for each interrupt, for each peripheral interrupt, right? Right. So to set the priority number for 240 of them, right? So 240 interrupts. How many bytes do I need to specify the priority for them all? What do you think? William 16? That's not correct. More answer, please. Quickly. Aha, Muhammad, 240. That's the correct number, right? As I said, to set the priority for each interrupt, you need a whole byte, not 1 bit anymore. Whole byte, right? For enabling, yeah, 1 bit, but for priority, 1 byte. So you have 1 byte for 1 interrupt. So you have 240 interrupt. You need 240 byte, and that's why in here you can see in C over here, I reserve 200 an array, a whole array, 240 of them, 240 element, and each element is a bit over here. See? Do you understand this one now? Right? So, for example, if you want to set the priority for the interrupt, external interrupt line 1, for example, right? So the interrupt number is 7, right? So you will store in this array, in the IP array, element number 7. That's all. So simple, right? Very easy. So if I want to set the priority for interrupt number 9, then you store that interrupt priority in the array IP and the element 9. That's all, right? Okay. So for example, now I want to set the priority for external interrupt line 1 over here, right? To 60, 0, 1, 1, 0. This is 6, okay? And because we don't use this one, so basically they are 0. So you can see in hex, this is a 6, 0. 6, 0, okay? So if I set that one, I just need to set that array element to 60 hex. That's all. So easy, right? Understand how to set the priority for the interrupt you care about? Okay? That's how you set the interrupt, right? Okay, so now next. This is for peripheral interrupts over here. Peripheral, okay? So now let me come back to the the system interrupt, right? How many system interrupt do you have? 16. Is that right? 16, right? And now, as I said, for reset, for non-mass interrupt, they are very, very important interrupt over here. And hard for interrupt over here, for these three guys, they are preset. This guy is, the priority is -3, this one is -2, this one is -1, right? -1. And you cannot change it, right? But you can change up here. You can change these 12, right? So because you have only 12 left then, right? So how many bytes do you need for the system interrupt priority over here? Can you tell me? Okay, now another question. Please respond. 12. Excellent. You have the right answer on the first try. Thank you so much. Yes, that's right. Right. So I will declare an array, right? The array, the name of the array is SHP. System something priority. I forgot what is it stand for over here, but that's as a system something priority over here. Okay. Yeah, you just need one array of 12 elements, and each element is 1 byte over here, right? So for the number, the interrupt number -12 over here, you will put it over here. You will put at element 0. The interrupt number -11 over here, you will put it over here, right? For -10, you will set the priority using element 2. Blah, 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 blah. So for interrupt system tick handler over here, interrupt -1 over here, I will put at the element 11 of this array, SHP array. See? Is that easy? Very easy, right? You have 12. 1, 2, 3, 4, 5, 6, and blah, blah, blah to 12. Okay? However, in C, you cannot tell C program, oh, I like to pick this one, right? Of course, I mean, looking at the picture is very easy, but how to tell C to do that? So you just apply this formula for me, right? So for example, if I tell you what element you will set to change the priority of the system tick over here, looking at the picture, you know right away, right? This guy will go to 11. But how do you know? How do you know in C? How do you tell C is 11 over here? So this is the formula over here. Okay, this is the formula. And let's check to see, check the field to see if you understand. Okay, so for example, in this case, -1, that's the interrupt number over here. -1 in two's complement number, right? What is that? -1 is over here, right? Right? 5-bit 1, 1, 1, 1, 1. 5-bit over there, right? Now you AND bitwise ANDs with the 0F, right? So what do you get? So now you will get 1, 1, 1, 1. 4, 1 only, right? Right? And 4, 1 actually in the number is 15, right? 15 minus 4 is 11, right there. Let's go to 11 right here. Okay. So let's check another one over here. So for example, if you pick this one, the interrupt number -12. So interrupt number -12 had to go to the element 0, right? So let's see if this one will give you 0. Okay. So yeah, actually it's true because -12 is 1, 0, 1, 0, 0, right? And if you end with F, the first one goes away and you only have 0, 1, 0, 0. And that's actually 4, right? 4 minus 4 is 0. So you can figure out the index over here easily. Okay? Understand? And then, I mean, as normal, the priority you want to set is here. For example, 6, for example, right? But because you have to shift by 4 because you don't use this one. So you have to shift that 6 4 times so that it go to the upper 4 bit over here of the byte, right? Shift by 4 to go over here. And that's all. That's how you set it. Okay. So one more slide, last slide over here. So let me. So this slide is actually used to enable or disable the interrupt. Okay. Disable a bunch of them at the same time. You don't have to go. This is very useful when you sometimes you write the interrupt handler, for example. So before you do something to be safe, you disable the interrupt first, and then when you after setting the whole thing, then at the end you enable them again, right? So this setting use these 3 registers will be very useful. Then you don't have to disable one by one. You just write something, use this one, for example, and you can disable a bunch of them at once. Okay, so let's go through one by one. Okay, so remember the registers that I already taught you, right? 13 general purpose registers, right? R0 to R12, and then stack pointer, programming counter, whatever link register, and then PSR, and the control. You also know the control registers, right? Just 3 more left. They are here. Okay, so up until this point, you know every register that we set up from lecture number 1. Okay, so what is a prime mask? So this is a priority mask over here. So if you put some number different from 0 number in here, for example, in this case, I just put 1 into the a priority mask register, right? It will disable everything everything from here, from -12 up, everything. Okay, see, just set this register to 1, you disable everything from up here except these 3. These 3 you will not, the last 3 over here, right? Except hard 4, NMI, and reset. Okay, but if you set the register fault mask to something different from 0, you can also disable everything from -13 up, everything up here, okay, except the NMI and reset handler. Okay, so they are very useful, right? So if you understand that, you can use to disable a bunch of interrupts here at the same time. Okay, so last thing is about the base priority interrupt over here. For this one, actually, if you can specify a number put some number in the base priority register, for example, 60. If you put 60 a hex in here, right? So it means that you will disable everything above 60, including 60. Every interrupt that has priority number 60 or above will be disabled. Okay, understand? So that's why this one is called the base. So anything below that one, you call that, you unmask. Okay, unmask. Mean that you kind of enable them. But everything equal to this number or above, right, will be masked, will be disabled, right? So if I set the base priority to, let's say to 10, 1, 0, what does it mean? It means that any interrupt that has priority equals 10 or higher will be disabled. That's the meaning. Okay, so with that, I like to stop the lecture over here. Any last questions? Last minute questions? Okay.
I was thinking why they may have had the priority where 0 to 3 is not used. Is it like a buffer or something where you want to store certain values? Keep, like, if something breaks, at least those 3 values back.
The idea is sometimes you like to disable a bunch of them at the same time without going to each one of them and disable one by one, right? It will be very tedious to do when you write the interrupt handler routine, right? So at the beginning you have to disable tons of interrupts, right? So using these are important. Less tedious, right? Instead of doing one by one, you can disable one of them at the same time, right? So just that. So let me see. Can you explain preemption priority again? Okay. So now, if they let me come back to that one again. So if preemption are the same, for example, right, for all 5 or 10 interrupt happening at the same time. So and if the processor is serving some interrupt at that time, right, that interrupt will not be stopped. It continues to run until it's done, and then the processor will pick the next one, right? However, if among 10, right? Among 10 interrupt happening at the same time, one of them is already serving. Is being served, right? But if somebody just come and that guy has a higher priority in terms of preemption, meaning has a lower preemption number, then that new coming guy will pick out the one that is being served. Okay, the processor can even stop the task that it is running to serve the new coming guy first, if that guy has higher priority in terms of preemption number. Okay, do you understand? Okay, very good. I'm happy that I can explain that one to you. Okay, so time is up. So I'd like to stop here. Thank you very much for your attention, and see you on Wednesday. Wednesday, I will release